Hi everyone, welcome back to another video with us here at LMDN STEM Academy. Please be sure that you hit that subscribe button so that you'll be first to know when we upload a new video. Now we'll be continuing with the part 2 of where we left off last time. So we were talking about determining molecular formulas. We had discussed how to do so from an empirical formula. And where we left off was then being able to do that determination from volumes of gases obtained from combustion data. So that will be the focus of our video for today. Determining molecular formula from volumes of gases obtained from combustion data. So let's think about where it is that we're trying to go ultimately here. Like, what do we want to achieve, right? When we're given volume data. So when we're given the volume data, right, you can imagine that it's from a combustion reaction. So the first thing that we'd want to do is be able to write just an equation, right, a generic equation that describes the process of combustion or combustion reaction. So let's imagine that we have a hydrocarbon, C, so it's made up of carbon and hydrogen. And for the moment, imagine that we don't know how many carbon atoms are in there. So we're going to just assign that as X. And we don't know how many hydrogen atoms are in this molecule. So we're just going to put it as Y, right? So what happens in a combustion reaction is that we have our hydrocarbon being reacted with oxygen gas, right? And you can imagine that our hydrocarbon would be in a gas phase as well, right? Depending on which hydrocarbon it is. So we have our hydrocarbon reacting with oxygen gas, and the products of combustion, right, are generally going to be carbon dioxide in a gas phase, right, as well as steam, right? So this is a very generic reaction that can describe the combustion process. It's not balanced just yet, but we just kind of want to see what's at play here, right? So when we're given volumes of gases data from combustion, they might tell us what volume of our hydrocarbon we combust. So maybe they tell us that we combusted 10 cm cube of that hydrocarbon. They might tell us that we did that with 50 cm cube of oxygen, right? And they might tell us that as a result of that combustion, we got maybe 70 cm cube of carbon dioxide or 100 cm cube of steam, right? They will give us some amount of these volumes, right, for each of these species. So we'll have volume of gases data. So now remember, when we're finding a molecular formula, really what we want to find, right, is the actual number of atoms that are in that molecule, whereas this is our molecule in question here, right? So ultimately, where we're trying to go is to find X and to find Y, right? So how is it that we're going to get there using volume data? Well, what we're going to do is we're going to start with our volume data, right? So those are all the volume data that they gave us in this row here. So we're going to start with our volume data. And what we're going to do is we're going to find a way to convert that volume data to moles data, right? And then when we have that moles data, specifically the moles data that we'll be seeking here is the moles of each species, right? So we'll be trying to fill out these parts. We're trying to find how many moles of this we have based on the volume, how many moles of that, how many moles of this, and how many moles of this. So once we're able to successfully get that moles data, or kind of like a stoichiometry, right, for this reaction, then what we can do then is we can then find the actual number of atoms of each element in that hydrocarbon. So I'm just going to write that here, that we're seeking ultimately the actual number of atoms of each element, right, in that compound, that or unknown compound, right? So effectively what we're seeking here, if we were to look at this compound, we're seeking to find what is X and what is Y, right? So that's the overarching goal. In any one of these problems that you get when you're given volume of gases data, you're always trying to convert that volume to moles. And then from the moles, right, these stoichiometric amounts, then we can actually figure out the actual number of atoms of each element in our molecule or a hydrocarbon here, which would be we're trying to find X and we're trying to find Y. Now, how do we get from here, right? How do we get from this point, step 1, to step 2? How do we get there? What should we do to go from here to here? Well, this is what we're gonna do. We are going to use Avogadro's law, right? We're gonna use Avogadro's law to make that transition. That's how we do that, right? And so now we have to have a discussion about Avogadro's law. So let's just have a little bit of a recap on Avogadro's law and think about how you might be able to use that, right? To go from a volume data to moles data, and then from there we can figure out the rest, right? So let's talk about Avogadro's law a bit right now. So Avogadro's law essentially states that equal volumes of gases at the same temperature and pressure that they contain the same number of moles, right? So let's take some hypothetical gases. We're just gonna imagine that we have hydrogen. So let me just kind of get a shape to show you, or to really represent like a container, right? So imagine I have a container here. So I have 3 containers, right? So imagine I have 3 containers, right? And let me clear this because I want you to see that the containers are of the same shape. So I'm just gonna take that one, right? And just kind of make some replicates of it, right? So here we are. Just gonna take this one. Take this one. And move it over here. And we'll just get rid of that one. Okay, so let's imagine that we have 3 gases. So we have 3 gases. You can imagine that we have the first one. Let's imagine that there's hydrogen in that container there. So there's H2 there, right? So let's do that. So imagine here we have H2 gas. Imagine here we have oxygen gas. And then imagine that we have steam, right? So we know that that's just gas phase water. So that would be steam, right? So imagine that we have that. And as I said, they're at the same conditions of temperature and pressure. So imagine that this is T, let's say it's 100 Kelvin. And let's say that this guy is also at 100 Kelvin, the oxygen, right? And the steam is also at 100 Kelvin. Pressure is also the same. Pressure has to be the same. So let's imagine that we are at 1 atmosphere, right? Or 760 millimeters mercury, right? That's another way that we can talk about pressure. And that's the same for all of these gases, right? So everything is the same. The temperature and the pressure is the same. All right. So I'm just writing that out so we can see that they all have the same temperature and pressure. Right? All right, so they have the same temperature and pressure. So what Avogadro's law is saying that if you have gases, right, they can be different gases, they can be the same gases. If you have gases, like we have H2 here, O2 and steam, as long as they're under the same condition of temperature and pressure, right, and they are in equal volume, like we see that these are the same volume. So let's say that the volume is 10 cm cube of that, and it's 10 cm cube of this, right? And it's also 10 cm cube of this, right? That's the volume of that. then what Avogadro's law says that they're going to contain the same number of moles. So the moles of H2 is going to be equal to the moles of O2, which will be equal to the moles of water. It doesn't matter the identity of the gas. As long as they have the same volume and they're under the same conditions of temperature and pressure, they're going to contain the same number of moles. So that means that if there were 1 moles of hydrogen here, then it would be 1 moles of oxygen as well, and it would be 1 moles of steam. Why? Because they have the exact same volume and they're under the same conditions of temperature and pressure, right? And this is very revolutionary and very helpful and can be a great way of connecting then a volume to number of moles, right? So this is a very useful thing for us to remember if we're going to be able to successfully make the leap from volume data, right, to moles data. So this is what we're going to use, right? Now, let's take an actual equation to just kind of show you how this comes into play, right? Because ultimately what we're going to be using are equations, right? So let's kind of put this in an equation form and see what we get from that, what we can glean from that. So let's write this equation here where we're forming steam from hydrogen and oxygen, right? So I'm going to write that we have 2 moles of hydrogen gas, and that is reacting with a mole of oxygen, right, to give me 2 moles of steam, right? So I can write that down underneath. I love translating these stoichiometric values into words, right? There's an imaginary 1 here, as you can imagine, right? And then, of course, it's 2. So if I were to translate what this balance equation means in words, I would say that there are 2 moles of the H2 that react with 1 mole of the oxygen. And from that, I'm going to get 2 moles of steam, right? No. Remember now, based on Avogadro's law, if they had the same volume, they would have all the same moles, right? But they don't. We can imagine then that they don't have the same volume, because if one is 1 mole and then one is 2 moles, it means that there's a difference between the volume that this one occupied versus this. In fact, it's twice as much in terms of its volume than this, right? Because 1 is 2 and 1 is 1. So we could say then that this represents there being 2 volumes present, right? And we can say that because this is 1 mole, we can say that that's 1 volume, right? And then, of course, this would be 2 volumes, right? All right, so essentially what we're doing is we're taking 1 volume to represent there being 1 mole, and then 2 volumes would mean that there's 2 moles, right? Because there's like a ratio that they're present in. And so we're gonna discuss this idea of there being different standards for temperature and pressure, and then room temperature and pressure. And then we would perhaps be able to assign some values to these, right, from a volume standpoint. But if we look at the stoichiometry can tell us how the volumes would differ, right? So you can imagine, let's just say for argument's sake that a 1 volume would be a 10 cm cube. Then 2 volumes would be what? 2 times that. So that would be 20 cm cube. And then this would also be 20 cm cube, right? So imagine the question tells you that you have 10 cm cube of oxygen, 20 cm cube of steam that you get, and that was from you reacting the oxygen with 20 cm cube of hydrogen. Then you would know that, hey, then maybe I could put these in terms of moles, and this would represent a 1 mole, and this would represent a 2 mole, right? Because that's 2 volumes. So that's how we go from volumes to moles using Avogadro's law, right? So that's really what we have here in a nutshell happening. Now, there's one more thing I want to touch on, as I said, regarding Avogadro's law. So let's clear this and we'll move on to that piece, right? So as it relates to Avogadro's law, right, we can talk about there being a standard temperature and pressure known as STP, and we can also talk about there being room temperature and pressure known as RTP, right? Now, STP means that we're at a temperature of 0 degrees C, pressure of 760 millimeters of mercury, and then 1 mole of gas will occupy 22.4 dm cube when we're under these conditions, right? And so you can imagine you get a question and they're telling you that you're at STP. All gases were measured at STP, so you know that they're under the same conditions of temperature and pressure, and each mole of that gas will occupy 22.4 dm cube, right? On the contrary, you can have something known as room temperature and pressure, right? And when we say we're at RTP, that's what we mean. We're at room temperature and pressure, where the temperature is 20 degrees C and the pressure is 760 millimeters of mercury. And under these conditions, a mole of a gas will occupy 24.0 dm cube, right? So if we know the conditions that we're under, right, and we're given volume information, we can convert that volume to moles, right? So this, if we're given a STP information or RTP information, immediately we can go from volume to moles, right? Readily, very readily we can do that. We can go from volume to moles, right? And that's because if we're at STP, we know that 1 mole of the gas would occupy 22.4 dm cube, right? So they can tell you that you have what? They could tell you that you have 2240, right? They could tell you that you have 2240 dm cube, and then you'd have to find out you can find out the corresponding moles for that, right? So that's kind of how we would do that. If we're given a volume and we know what conditions we're under, right? We'll know how to find the moles from that. And then similarly for RTP, if you're told that you're at RTP, 1 mole is going to occupy 24 dm cube. So if they tell you what volume of the gas you have, then you can figure out how many moles of the gas you have. And then now we can progress to find out the actual number of atoms, which will give us our molecular formula. Okay, so in light of this information here, we're going to take some examples and just kind of apply all of it. So put it into application, right? So let's clear this and keep moving forward. So what we're going to do right now is we're going to take our first example, right? So here's our first example, example 1. When 20 cm cube of a hydrocarbon reacts with 160 cm cube of oxygen, 100 cm cube of carbon dioxide is produced, and the other product is steam. So they want us to use all of this volume data to deduce the molecular formula of the compound, right? Now, a key assumption here when they give you these volumes data, just like this, the key assumption here is that you're under the same conditions of temperature and pressure. We don't know explicitly if we're at STP or RTP because they didn't tell us that, but we do know that we're under the same conditions of temperature and pressure for all of the gases, the volumes that they gave us here, right? So that's an assumption that we can make in order to apply Avogadro's law, right? So step 1, what we're going to do in step 1 is we're going to write an equation showing the combustion of the hydrocarbon and then write the corresponding volumes that they gave us up here underneath each compound, right? So here's what we're going to do. So let's write the equation, right? So imagine we have the hydrocarbon. We don't yet know the amount of each atoms that make it up, but we know that there's going to be a carbon in it and there's going to be a hydrogen in it because it is a hydrocarbon. So let's just assign X for carbon for now, the amount of carbons, and let's assign Y for the amount of hydrogens. Now, of course, it's a combustion, so you know we're going to have our oxygen gas here as well. I'm going to put a gas here. And then what else? We're going to form carbon dioxide as the question tells us, and also steam as a product, right? So we write out all of these here in that, initial equation rather. It's not balanced just yet, but it's just the initial equation that describes combustion that we're writing. We're going to write the volumes underneath each of them that they assign. So they said that we're going to combust 20 cm³ of the hydrocarbon with 160 cm³ of oxygen. And we're gonna form 100 cm³ of carbon dioxide. So that's all the information that we have. They didn't give us any information about the steam, okay? So we're gonna leave that part blank for now, okay? All right, so let's go to step 2. Step 2 says we're gonna find the simplest ratio of the gases and use Avogadro's law. So here is where we're gonna look at the volumes that they gave us and where we wrote them. So we wrote 20 cm³ under here, 160 here, and 100. So you can imagine that they're all related by some factor, right? They're not the same volume. So we know that the coefficient that we're seeking, right, for here, here, and here, we know that those coefficients are going to be different, aka the number of moles of each of these species is going to be different because they have different volumes, right? But what we need to determine is like what ratios are they in with each other. And we can see that this is a nice little setup here where these numbers, right, are all multiples of 20. So if we take 20 as our base number, what we can do, right, is we can divide through all of these by 20 to get what the ratio is. So if I divide this one by 20, right? If I divide the 20 by 20, use this color. If I divide the 20 cm³ by itself, of course, you know that that's just 1. So that will let me know that there's like a 1 mole that I can put here for my stoichiometric coefficient. I can put a 1 here, right? And then for the oxygen, there was 160 cm³ of it. So if I want to find what combination or how much is that, what's that factor that connects it with the 20, I'd have to divide it by the 20, right? And so then we'll see that here, so this was 1, right? And this would give us what? 8, right? And then similarly for the 100, if I do 100 divided by 20 cm³, right? I'm gonna get what? That there's a 5 there, right? So what that means is that there's 1 mole of this, there's 8 moles of this, and there's 5 moles of this. So I can put them there now. So I'm gonna put my 5 here. Actually 8 is supposed to go there. So I can put my 8 here for the oxygen, right? That's what that was that we got there. And then the 5 for the carbon dioxide. So I put that there. Okay? So you can see what's happening here now is that we're kind of filling out, right, the equation that we had written initially with some coefficients, right, some stoichiometric coefficients. So that's what we're doing. So that's the first step, that we went from the volume to moles, right? So now we're there. And so what we can do is we can balance this equation thinking about the oxygens, right? So if we look here, we see that 8 times 2, there are 16 oxygens here, right? So there are 16 oxygens right here. And then here, 5 times 2, there are 10 oxygens here. And so if we want this to be balanced in terms of oxygens, and there's 16 here and 10 here, then it means that this one has to be a 6. So we have to put 6 here, okay? For the stoichiometry to work. So when we do that now, we have 6 oxygens here, 10 here, so that's 16 in all on the right. And then there are 16 here, so that's 16 on the left. And so our oxygens are balanced, right? So now we can move to step 3, which is the deduction step, where we're deducing the number of oxygen atoms and the number of hydrogen atoms using the stoichiometry that we've established here. Okay, so let me just erase these guys for now that we use for this to figure out the stoichiometry. And so what we're gonna do now is we're gonna just zero in on carbon, right? Let's zero in on carbon. So we're gonna write here now, for carbon, we're working on carbon first, right? So for carbon, what we're really trying to do in this deduction step when we're trying to figure out number of carbon atoms is we're trying to figure out X, right? And so you know that based on the conservation of mass or how balanced equation work, is that whatever amount of carbon atoms that you have on the left, you have to have the exact same on the right. Essentially, any carbon that's over here had to have come from here. right? And so if we want to figure out the number of carbon atoms, we can say, start by saying that the left-hand side of carbons has to be equal to the right-hand side, right? And so what we're gonna do is we're gonna say, okay, how many carbons does this say here? We're gonna have to multiply the stoichiometric coefficient by the x. So we do 1 times x, because that will be the total number of carbons over there. And over the right-hand side, now we're gonna have to say 5 times this imaginary 1, right? That's right there. So it would be 5 times 1, right? And so that will lead us to saying then that x is equal to 5, right? Because if there are 5 carbons over here, there has to be 5 here where these came from. Okay, so that's how we deduce that for carbon. Now let's do for hydrogen, right? We're gonna still apply the conservation of mass. So whatever is on the left-hand side for hydrogen, they all had to end up on the right-hand side, right? So on the left-hand side for hydrogen, we're gonna do 1 times y, right? So we're gonna multiply this 1 times this y here. And then on the right-hand side, we're gonna do the 6 here, and we're gonna multiply that by the 2, right? That's the total number of hydrogens over there. So we would have 6 times 2. And so from there, what would we get? We would get that y is equal to 12, right? And so if we take this CXHY where we didn't know X and we didn't know Y, we now know them, right? So that compound will now be C5H12. So that is the molecular formula of the compound, right? We didn't know what it was initially, but through using the volume data and converting the volume data to moles, and then from deduction, we were able to figure out this molecular formula, right? Now, finally, the last thing that we're going to do now that we know what the X and the Y are, we're going to put it all together. So essentially, we're just going to rewrite this equation, but what we're going to do is we're going to put in the 5 and the 12, right? So what we can do is we can actually come back up here and take out the X now and take out the Y now, because we know what they should be now. They should be a 5 and they should be a 12, right? And so when we look at the balanced equation, now we see that everything works out. There are 5 carbons over here, there are 5 over here. There are 12 hydrogens over here, there are 12 hydrogens over here. There are 16 oxygens here, and they are 10 plus 6, 16. So that's our answer, okay? So this is what we were seeking all along, our molecular formula, and we were able to get that, okay? So now, we're gonna do another example. So we're gonna move on to example 2. And if you need to just pause here for a bit and just like take notes of all the steps here, we're gonna then move on to doing the other question, okay? So let us move on, right, to example 2. So for example 2 now, it's very similar to the one that we just did, where we're given that we have 60 cm³ of oxygen, and that is required for the complete combustion of 10 cm³ of a hydrocarbon. So again, we know we have a hydrocarbon, only carbon and hydrogen makes up that compound there, right? So we can start to take notes as we read so that we can see what's going on. Hydrocarbon, right? So that will be a CXHY, because we don't know, right, how many carbons and how many hydrogens we have, but we know it's a hydrocarbon. So we're gonna use 60 cm³ of oxygen, and that's what's required for the complete combustion of 10 cm³ of a hydrocarbon, and then 40 cm³ of carbon dioxide is produced as a result of that combustion. Now they want us to determine the formula of the hydrocarbon and then deduce the balanced equation for the reaction, right? So let's get started here. What we always do is we want to always orient ourselves. We always want to write just a general equation that describes the combustion that's going on, right? So that's our step 1. So what I'm going to do now is I'm just going to write CXHY. That's our hydrocarbon that we don't know the formula of just yet. But we do know that it is being combusted with oxygen, right, to form carbon dioxide gas. And we also know that steam is going to be a product as well. They didn't tell us that, but we know that we're going to get steam as well. Okay, because these hydrogens have to go somewhere, right? So our only product can be carbon dioxide. So we have to write our steam as well. Okay, so now that we have that general equation of what's going on, we can assign the volumes that they gave us to each of these compounds here. So they told us that there's 60 cm cube of oxygen that was required for the 10 cm cube of the hydrocarbon, and that we would end up getting 40 cm cube of carbon dioxide. Now remember, look at these volumes now. You see that they're nice multiples of each other? They're not the exact same volume. They're multiples of each other. So we can see that 6 is a multiple of 10 and 40 is a multiple of 10. So if we take 10 as our base and we divide everything through by every one of those volumes through by 10, we can come up with our stoichiometry or our number of moles. So that would be 1, right? So we would put that 1, take that 1 that we just got and put that here, right? For oxygen, we do a similar thing. We're going to find the factor that connects that volume of oxygen to this base of 10, that one volume of 10, right? And so we'll see that we get 6, right? So that's what we're going to put here in front of the oxygen. And then finally, for the carbon dioxide, we're going to say, okay, 40 cm cube divided by the 10, right, to connect it to that base volume, that one volume. We see that here we actually have 4. So we have 4 volumes, and that's equivalent to there being 4 moles. So we put a 4 here. Okay? All right. So now we have stoichiometry coefficients for all of these species except hydrogen, right? We don't yet have anything for hydrogen, but we can balance that, right? We can. We don't have anything for the steam, that is. So we can balance that because we know how many oxygens there are. We know that over here, there are what? There are 12 oxygens. Over here, there are 8 oxygens. And then, so there has to be 4 that have to be accounted for, right? So 12 over here and 8 over here. But in all, there has to be 12 over here. So we know that there's a 4 that needs to go here. Okay? So now the 4 and the 8 would make 12, and it was 12 that we started with, so we have to end up with 12 being over here. Okay? So just put 4 here. Right, so that's 4. Right? Okay. So now we're ready to deduce, to do our deduction, right? So that's our next step. Our next step is the deduction. Our second step was to find the simplest ratio. So let me just number the steps here. So if you're following along with the steps, you can follow. So that was step 2, was to get the ratios. Now we're at step 3, where we're doing the deduction, right? We're deducing the number of carbon atoms, C atoms, and we are deducing the number of H atoms because we want to find X and we want to find Y. Right? So let's take carbon first. So for carbon, right, what we can see is that on the left, there's a 1 times X carbons, and then on the right, there are 4 carbons, right? We say 4 times the 1. So that's going to be equal to 4 times the 1 that we have here, imaginary 1 there. You can imagine that, right? So it'll be 4 times 1. And then as a result of that, we know that X has to be equal to 4, right? All right, so let's do the same thing for hydrogen now. So for hydrogen, right, on the left-hand side, we see that it's 1 times X times Y. So it's 1 times Y for hydrogen, 1 times Y. And then that's going to be equal to what's on the right for hydrogen, which is 4 times 2. So we do 4 times 2. And so from that, we find out what? Y is equal to 8, right? Y is equal to 8. So now we know what X is and what Y is. So if we were to write our CXHY, then we will see that that is now C4H8. And that is the molecular formula of the hydrocarbon. This is what we were seeking all along, so we got our answer there. Okay? So finally, they want us to deduce the balance equation. So for that, we're going to just go back up top here. We're going to go back up top here, and we're going to replace our X and our Y with what we found. So we're just going to stick in what? 4 for carbon right there, right? And we're going to stick in the 8 for the hydrogen for Y, where Y was. And so when we look at this, we see that it's balanced perfectly. So this is the balance equation that they wanted us to deduce ultimately after finding the molecular formula. So there are 4 carbons over here, 4 carbons over here, 8 hydrogens over here, 8 hydrogens over here, 12 oxygens over here, and then what? 8 plus 4, 12 oxygens over here. And so that's our answer. Right? So just always remember to go through those steps. You're writing out the shell of the equation, and then you're converting the volumes to ratios or mole ratios, and then you're just going to put those in front of your respective species. And then now, finally, we're going to do our deduction, right? Where it's based on conservation of mass, your left-hand side has to be equal to your right-hand side. So that's what we did here. Okay? All right. So now, what we're going to do now is I'm going to clear this. And if you're still with us and you haven't subscribed and you haven't liked this video, take a moment now to like the video, to subscribe to the channel. And now we're going to take it up a little notch. We're going to take it, we're going to complicate this a little bit more. Okay, so let's move on to that one. So in light of all that we've covered up to this point, right? You can imagine a scenario where you're given a combination of data. Imagine that you're given a combination of Avogadro's law and mass data, right? So last time we spoke about what we need to do with the mass data to get it into a moles form. And so we're going to combine those concepts right now, right? So this is our final example for today, example 3. So example 3 says that mass spectrometric data, right? So that's a technique and analytical method. And using that method, they did that on a compound Q, and it was revealed that that compound had a relative molecular mass of 108, right? Now, when they did elemental analysis to figure out what elements are in compound Q, they found that the elements present were carbon, hydrogen, and one other element. Ooh, very mysterious. We don't know what that other element is as of now, but we do know there's carbon and hydrogen there, right? So if we're like writing out notes as we go along, we know that there's carbon in here, there's hydrogen in here, and then there's a mystery element, right? Now they're telling us that when 1.08 grams of compound Q is completely burnt in oxygen, so it's a combustion of some sort, the products contain 1340 cm cube of carbon dioxide and 448 cm cube of nitrogen dioxide measured at STP, right? So they're telling us the products that are forming in this unique case, and they're telling us that it's measured at STP. So because they told us that it's measured at STP, immediately we can write that we know that 1 mole of a gas under that condition will occupy 22.4 dm cube, right? So we're just like orienting ourselves and writing down everything, every piece of information that we're given from here, okay? So let's proceed with the stepwise approach that we've established today to do this kind of an analysis. So let's write our step 1. What will our step 1 be? Our step 1 will be to come up with, just write the general equation that represents its combustion, right? So we're gonna write, let's just write compound Q here for now, because we don't know all that is in it, right? Just yet. So we're gonna write compound Q. That compound is being combusted, so we have it reacting with oxygen, right? And then what we're gonna get, they told us the products that we're gonna get carbon dioxide and nitrogen dioxide. So we're gonna write those compounds here, their formulas, right? So we write carbon dioxide and we write nitrogen dioxide, right? And then of course, guys, there has to be steam as well, okay? There has to be steam because we know that there's hydrogen in this compound, and the hydrogen generally forms, combines with the oxygen to form steam. So we need to have that as well, even though they didn't list that as a product, okay? All right. So let's look at compound Q now. They told us that we have carbon in there, so we don't know how many, so we're just gonna call that the amount X. We don't know how many hydrogens either, so we're just gonna call that Y. And they told us that there's like a mystery element. And if we look at our equation that we came up with, right, using the information that they gave us, we saw that there's this N, right? Where must have this N come from? It must have been in the compound Q as well. So we're gonna put N as our mystery element. We figured out our mystery element and it's N. So we're gonna put N here in compound Q. We're gonna put a Z beside it because we don't know how many nitrogen atoms there are in compound Q, but we know it exists because the nitrogen dioxide had to have come from that, okay? So we figured out our mystery element. So what remains for us to do now is that we're just gonna write out the volumes underneath each of them as we've been doing before. But you may notice that for compound Q, they didn't give us a volume, right? They said 1.08 of that compound is burned. So what we're gonna put underneath the compound Qs, we're just gonna put the mass. It's 1.08 grams that they told us that was burned. And then everything else we're going to put volumes for, right? So the volume of oxygen, they didn't tell us, but they told us that we were able to form 1340 cm cube carbon dioxide and 448 cm cube of nitrogen dioxide. Didn't tell us anything about steam, so let's leave that one blank for now. Okay, here's where it gets a little bit interesting. So in all the examples that we've done so far, right, they didn't specify what conditions we were under. They didn't tell us whether we were at STP or RTP, but now they have. And so what this means is that we can directly convert these volumes to moles, right? We can directly convert them to moles, directly using this molar volume of 22.4 dm cube, right? So we can directly convert those to moles. And as it relates to the mass of compound Q that they gave us, we can directly convert that to moles as well, right? How do we go from mass to moles? We would divide the given mass, right, by the molar mass. So we would divide that given mass of 1.08 by 108 grams per mole that they told us that that is the relative molecular mass. And when we do that, we're going to come out with a mole of, we're going to come out with a mole here of 0.01 moles, right? That's how many moles of compound Q we combusted. Okay, moles of Q. And so let's do these conversions now from volume to moles, given that we're at STP. So because STP is quoted, the molar volume is quoted in 22.4 dm cube, what we're going to do is we're just going to convert these guys to dm cubes first. So that would be equivalent to, I'm going to divide this by 1,000. That would be equivalent to 1.34 dm cube if I do that conversion. And this one will be 0.448 dm cube. So now we're ready to work. We know that 1 mole of that gas would occupy 22.4 dm cube because we're at STP, right? So it occupied 22.4 dm cube. So how many moles do we have if it is that we have 1.34 dm cube? Right? That's really what we're setting up here. That's really what we're doing. And so it turns out that that actually translates to what? So if we do our cross multiplication, we're going to find that X moles is equal to, that's going to be, bam, 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 bam. We were to cross here. We're going to find that X is going to, the X moles is going to be equal to 1.34 divided by the 22.4, right? And that's going to get us 0.06 moles, right? And we'll do a similar thing over here. Essentially, the number of moles is going to end up being equal to the 0.448 dm cube of it that we have divided by the molar volume of 22.4, right? And that's going to give us a mole of 0.02, right? Moles. So we don't want to put these numbers. Let's just highlight numbers that we have. We have a 0.01 for Q. We have 0.06 for the carbon dioxide, and we have 0.02 for the NO2. We don't want to put these decimal numbers in our, in our stoichiometry, in our equation here. And so what we're going to do is we're going to divide through by the smallest of these so that we can get some whole numbers, right? So if we're going to be dividing everything through by 0.01, it will end up that this is 1. So we're going to do 0.01 divided by 0.01. We're going to get 1 mole of that. And then if we divide 0.06 by 0.01, we're going to get that there's 6 moles of that, right? Carbon dioxide. And then this one, similarly, we're going to divide that through by 0.01. And that will mean that there are 2 moles of that NO2. So now we're ready to just bring these numbers up to their respective places in the balanced equation, right? So let me just kind of take this compound Q out from here and just bring up our equation form or formula without the respective values. We're just going to bring this guy up so it's in line with the others, right? So let's just bring this up first. I'm going to bring it up here. All right, so there we go. All right, so let's put the stoichiometric ratios in now. So this guy, Q, we found it was 1 mole. Oxygen, we didn't know anything about, so we're going to have to leave that blank for now, right? Carbon dioxide, we found that we have 6 moles of it based on the volume that they told us was produced. And for NO2, we found that there's 2 moles of that. Didn't have anything for the steam, so we're going to leave that for now. Okay, so now we're putting everything together now. We're ready to work, right? So what is the next step after this? What is the next step that we're going to do? Let's just bring these guys up as well, right? Let's bring them up here, right? Bring them up there. All right. So what are we going to do now? Let's look at what we have. Let's look at all the information that we have, right? So we don't know a coefficient for the oxygen and we don't know a coefficient for the hydrogen. So let's just work with what we do know though, right? We do have a coefficient for the carbon, so we could deduce how many carbons were over here, where this came from. We do have a coefficient for the nitrogen, so we can deduce how many nitrogens there are. So that's what we're going to do. Let's just take that approach first, right? So let's see here. We're going to do that, right? So we're going to say for carbon, right? On the left-hand side, it's 1 times x. So we're going to do 1 times x. And for the right-hand side, it is 6 times an imaginary 1, right? So it would be 6 times 1. And so that deduction lets us know that x has to be equal to 6, okay? Let's do the same for nitrogen now. For nitrogen, right? We know on the left that there's 1 times Z, and that is equal to 2 times that imaginary 1 there, right? So that's 2 times 1, and so that'll be that Z is equal to 2. All right, so there's one thing that we don't know now. So we know X and we know Z, but we don't know Y. Right, so let's start to fill out this with what we do know. We know 6 is X, so let's take out X and put 6. We're going to take out X and we're going to put 6. Right? We don't know Y, but we know Z. We know that Z is 2, so we're going to take out that Z and we're going to put a 2 there, right? So let's put a 2 here. All right. So the only thing that remains for us really to figure out as it relates to the molecular formulas, we have to figure out what Y is, right? How can we do that? we know that if this is 1 mole of the compound Y, then when we add up, right, the relative atomic masses times the amount of that atom that we have to end up getting the molecular mass. So we can kind of make it an equation that we can solve right now. So let's do that. So we know that if we do 1 times the relative atomic mass of carbon, I'm just going to put it there. I'm just going to put the 12 instead of putting in that. So we do 1 times 12 for the carbon plus the 1 Y, we don't know, because we're going to put Y times the mass of hydrogen, which is 1 plus 2 times the mass of nitrogen, which is 14, that all of that has to add up to 108, because that's literally what a relative molecular mass is. It's the sum of all of the relative atomic masses in the proportions that they're present. So right away, what do we have now? We have that Y, right? We can rearrange making Y the subject. We have that Y is then equal to 108 minus what? Minus 2 times 14, so 28 plus 12, right? Well, there's 6 carbons, so this has to be 6, right? So 6 times 12 rather. 6 times 12 here, so that would be 72. Okay? So there are 6 carbons, so we do 6 times 12. There's 1 hydrogen, so we do Y times 1, right? Which is the molar mass of hydrogen. And then we do 2, because there are 2 nitrogens. We do 2 times the molar mass of nitrogen, which is 14. And so that will then be equal to the 108, which is the relative molecular mass of the compound, right? So we rearrange now because Y is the only unknown. Y is the only thing that we don't know. So we're going to take the Y and make it the subject. So leave it on a side by itself. We're going to bring over everything else. So we bring over the 28 from here and we bring over the 72 from here. And so now what we're left with is that Y times 1 is equal to 108 minus 100, which is then equal to 8. So we know that Y times 1 is equal to 8, which means that Y itself is 8. And so now we can go up here, and wherever we see Y, we can take it out. Let's take out Y and put in the 8. All right. So there we have it. That is the molecular formula of compound Q. So it's actually, let's write it here. It's C6H8N2. All right. So that is the molecular formula of our compound. And let's look at this balance equation now and see if we can figure out the missing stoichiometries that we had here. All right. So let's see if we can figure that part out. All right, so we have 6 carbons over here. We have 6 carbons over here. We have 8 hydrogens over here. We're only showing the 2, so we know that we have to put a 4 here, right? For there to be 8 hydrogens here. So there are 8 here, so they have to be 8 here as well. Nitrogen, there's 2 here, there's 2 here. Oxygen, so let's look at the right-hand side since we have a coefficient for every species on the right. If we look on the right, we see that there are 12 oxygens here, right? And here there are 4 oxygens because it's 2 times 2. And then here there's 4 oxygens. So 4 and 4, 8. 8 and 12, 20. So there are 2 here. So that means that we have to put a 10 here to make it 20 in all over this side. So this would be our balance equation, right? 1 mole of compound Q reacts with 10 moles of oxygen to form 6 moles of carbon dioxide, 2 moles of nitrogen dioxide, and 4 moles of steam. Okay, so that's it, guys. So this was a very comprehensive question that really, relied on our understanding of just like what really is our objective when we're given any kind of information, right? We're given a combination of mass data and we're given volume data, and they told us that we're at STP, right? So what we did, we wrote our generic equation, we converted the mass to moles, the volumes to moles, right, using the molar volume here. And then we were able to then do some deduction to figure out the missing values of X, Y, and Z. So definitely pause if you need to, just sit with everything and make sure that it's clear. And if you've gotten this far, definitely give me a thumbs up, drop a comment down below and let me know if it's all making sense for you. And I'll be happy to discuss anything further, okay? So definitely share this video with your friends, like, comment, subscribe, and we'll see you in the next one, okay?